Hello, welcome back to another tutorial. In this one we're going to take a look at what's known as PBR Materials, or otherwise known as physics-based rendering. And first of all, without doing anything in Substance Painter, we're going to try to understand what PBR materials are and how they are manufactured and how they work essentially. Alright, so I have textured my shipping container here, and as you can see it has full materials like all around, including the bottom, and it has decals, text, the textures, the patina of the surface. It's all there. It is complete as far as I'm concerned. And let's look under the hood. Let's see what is going on. So in order to understand what is going on, first we have to look at materials from a different perspective, because materials, as we recognize them in the digital world, are not made out of a single texture. They are made out of multiple textures. In this case, several maps are utilized in PBR textures, as this article calls it, but we're going to be concerned mostly with this top four: the albedo, normal, roughness, metalness. That's it. You can include other textures, other maps for controlling the surface properties or reflectivities, in general how it reacts with light, using these maps, but we're not going to be concerned with those yet. So what's first on the list? It is the albedo map. Albedo map is just the color without anything, without light, without shadows, without anything that could affect its properties, affects how it looks. So right now in the Substance Painter I am in the material view, and that means that I am seeing everything, including its reaction to light. Okay, and it is updated in the UV map as well, because these things are related, obviously, after all. So if we go into single channel base color, this is basically albedo. Base color and albedo are the same thing. It is sometimes, albedo is sometimes referred to as base color or simply color, but both of those terminologies or nomenclatures are acceptable. This is just color, nothing else. Okay, so as you can understand pretty quickly that just color doesn't cut it, because color doesn't tell us how a surface reacts to light, how it shines the light, how it absorbs the light, how it diffuses the light, where does it shine it towards. Those things have to be defined using other textures. So in terms of, for example, where it shines the light towards, meaning that once a light source bounces off this surface, towards where does it go, we are referring to the normal map. Now normal map, I mean, this explanation might not mean anything. Normal 0 is just basically a shiny surface, a ball, and normal 1 is just crumpled paper. This doesn't tell anything, but probably this will. So a ray of light, once it reaches a surface, it is going to bounce off in the same angle. This is the actual surface, and this is the surface normal. The surface normal is vertical to the surface in all positions, meaning that if the surface was circular, then or surface was a sphere, then the surface normal would be concentric to the center of that sphere. Okay, so surface normal is a vector that is vertical to whichever position it is located at, and that a ray of light that reaches that point will bounce off in the same angle relative to that normal. So normal map, what does it do? It changes the direction of that vector based on color data. Color data that is recorded or saved or is referred to as RGB, red, green, and blue. A combination of those colors can be then translated into XYZ data, which can offset the direction or the angle of a vector, a surface normal. So in a manner of speaking, you are changing how the geometry reflects the light without touching the geometry, without changing the geometry. You're just changing where that towards where that geometry is going to shine the light. Okay, so this is the normal map, and when you combine it with the material in general, you can see that the normal map, where it's affecting the surface, you can immediately see its effects. Especially pay attention to the edges and how it shines the light different than those areas around it. But the geometry isn't changing. The geometry is just there. It is just a bunch of polygons facing the same direction, but the normal map is altering that direction. So that's what a normal map does. Next in the list is the roughness. So roughness is pretty easy. If your roughness is 0, that means that the surface is not rough at all. It is fully shiny. It reflects the light in a manner that will create specular highlight, what we refer to as specular highlights. So it is going to focus the light, or take a focused light source and reflect it in a focused manner. But if the roughness increases, then the light that hits that surface will scatter. It will start diffusing. It will go in multiple directions. So that will cause a rough surface. Okay? So let's look at the roughness map in Substance Painter. Now, this map, unlike the normal map, is not a color map. It is black and white data, meaning grayscale data. So white areas are completely rough. It is fully rough. And black areas are fully shiny. And any value in between is in the middle ground. So roughness data, you can see its effects on the material as well. When I change the light direction, not the base color material, when I change the direction, take a look at this surface particularly. It doesn't shine the light. It doesn't specularly reflect the light in the same amount. Some of those areas are more diffusey, are more scattering than others. Okay? So this is the effect of a roughness map. Particularly pay attention to these dirty areas, these stains on the surface. Those are definitely not reflecting the light in a specular manner. Because when you look at the roughness map, those are almost fully white, meaning that they are diffusing the light, fully diffusing the light, instead of giving off a specular reflection or a focused reflection. Okay? So what is next in line? It is the metallicness or metalness map. We refer to as metallicness, metallic map, or metalness map, or metal map, whatever you want to call it. So metallic 0 means that this surface is plastic in nature. We shouldn't really call it plastic, because plastics aren't the only non-metallic surfaces in the world. We usually call non-metallic surfaces dielectric, meaning that they are not conducting any electricity. So you could refer to this map as conductiveness almost, meaning that anything that is metal will conduct electricity, anything that is not metal will not conduct electricity. Obviously, there are middle grounds in the world. I mean, substances in the world is not made out of just metallic or non-metallic properties. There are semiconductors, for example, materials, molecules that conduct electricity to some degree or under the right circumstances. So those will not, you can create those types of materials as well, but mostly for our purposes, our metal maps will be in the binary range, meaning that it is either metalness 0 or metalness 1. Something is either metallic, metalness 1, or non-metallic, metalness 0. So what do we do with the values in between? Well, the values in between will be mostly used by the alpha maps. So if you go to the metallic channel, you will see that this system is almost binary. As you can see, things are either fully black or fully white. but the transitions have to be smooth because this is a texture map after all, and if these transitions weren't smooth, they would be pixelated because we are dealing with pixels. So the transitions will have to carry gray values in order to ease our eyes into this realistic looking material in general. But mostly we don't paint anything with gray when it comes to the metalness maps or metallicness maps. So that's the idea. But what does metallicness do? Well, in order to visualize what metallicness maps do, let's go to the very bottom of this stack and look at the base metal, which is just a uniform surface. So this is just a steel, let's call it a steel. It has a base color which is uniform, which means it is homogeneous all the way around this surface. There is no single one pixel that is different than the other. Every value is exactly the same. Same goes for the height channel, same goes for the roughness channel, and same goes for the metallicness channel. So as you can see, it is all the way up to 1. The roughness, it is almost fully specular. It is almost fully glossy, let's call it that, because the opposite of roughness is glossiness. So it is almost fully glossy, but see what happens when I reduce the roughness all the way down to 0, meaning that this object will turn into full glossy. It is going to turn itself into a mirror. This is a 100% reflective mirror right now. I mean, if the base color was white, then we are talking. This is full 100% mirror. No object like this exists in the real world because even the best made mirrors, the best manufactured mirrors in the world, such as those used in scientific applications, they're only reflective up to like 99.7%, and your run-of-the-mill ordinary house used mirror will be like 98% or 97, 96% reflective. Basically, it is very hard to achieve a reflectivity level closer to 100%, and it is impossible, certainly impossible, to achieve it at 100%. So we don't do these kinds of reflections, obviously, if we are looking for realistic materials. So let me crank this up to something more respectable, but let's look at it from the other way around. Let's make this super glossy, but then reduce the metallicness. When you reduce the metallicness, the object will keep being glossy and to some degree, of course, reflective, but it is not going to reflect its surroundings as if it is a mirror. It will start reflecting it as a ghosted image. So this is how plastics behave in general. They don't reflect their surroundings like metals do. So a mirror, in fact, is the reflective qualities of a mirror, for example, does not come from the fact that it is glass. There is a coating behind that glass that causes those reflections. That coating historically was made from silver. Today it's made from actually more manageable, more easily acquired and cheaper materials such as aluminum or pewter. But basically speaking, the reflectivity of the mirror is attained or is achieved, let's say, with metallic substances, not the glass itself. So this is what happens when you combine materials with the create materials with roughness and metallic channels. Those two work in tandem. Those two work together in order to control how the light shines off of this surface. One of them controls the glossiness of the surface, causing specular highlights or diffusing. The other one controls the reflectivity, how reflective the surface is. So at both ends of the spectrum, fully glossy, non-metallic, and fully glossy and fully metallic, you will get unrealistic results, obviously. Or fully rough is also very unrealistic. I mean, something can be fully rough, but fully rough and metallic at the same time will also not result in a very realistic surface or material finish, because a fully rough metallic part is also very hard to create. So that's the idea. You will have to find your own settings in most of these situations. Finally, we have another map. Let's go to the entire thing here. Open up the entire stack. Okay, everything open. Yes, it is. So finally, we have another map, and that map is the height map. We're not going to use the height map because height map usage or utilization requires other settings, meaning that you will have to change the geometry automatically or set up your software, whatever that software may be, Maya, Unity, Unreal Engine, wherever you're putting this object in, it will have to be adjusted accordingly in order to accept these height maps, because height maps change the geometry. They are specifically tasked with changing the geometry at the rendering stage, not before the rendering stage. It will not change your model. It will not alter your model in any way. But when your model is rendered, whether it's real-time rendering, like those things we use in game engines, whatever that game engine might be, Unreal, Unity, everything, or maybe you're into visualization and you're using rendering engines, biased rendering engines like V-Ray, Arnold, Mental Ray, Corona, Cycles, whatever you want to use. You can utilize height maps to alter your geometry after the fact. And these things are basically like real height maps you would find of the Earth. So let me show you a height map in this project. So this is the height map. It is very simple right now and it doesn't have to contain much. Okay? But you can see its effects. So this geometry right now, I mean, maybe you can't see it, you see its effects. So let's go to texture set settings, shader settings. Yes, my bad. Okay, so let's go to displacement and tessellation, and let's increase the displacement scale, and let's increase the tessellations because we have to. Now you can see its effects. I mean, this is extremely exaggerated, obviously. But you can see what it does. Basically, it modifies the geometry by subdividing it into further polygons, and it does that behind the scenes, meaning that, once again, it is not going to alter your model. It is not going to modify your model at an object level. It is going to alter it during rendering, and it could be pretty useful in some cases, and some game engines actually utilize these types of height maps very well, especially Unreal Engine version 4. Latest version was 4.27, but for example, Unreal Engine version 5 is trying to stay away from height maps or displacement maps, as they're otherwise called. It is trying to stay away from displacement maps as much as possible because it is a waste of time in terms of Unreal Engine 5's new rendering system, meaning Nanite. Nanite could not perfectly utilize displacement maps or height maps, so it is a relic of the past. It is slowly becoming a relic of the past, something we're not trying to visualize in rendering conditions, but maybe utilize for changing the actual shapes of these geometries as we are recording these objects as distinct models. So that's what a height map does, but that's about it. We are not going to be concerned with height maps in any shape or form. We're not going to deal with them, but you should know that they exist. So when these maps come together, they can create pretty interesting surfaces. So these are from the textures.com. Textures.com is a famous site in the industry. It is widely used for photographic references, photographic textures, whatever you want to call them. It also has a collection, a small collection of PBR materials that you can see. And these are all obviously not free. You have to buy them. You have to get credits, buy credits first, and then use your credits to acquire these substances, these materials. You can get the compiled material for 100 credits, or source file, which will allow you to modify this entire object inside Substance Designer, not the Substance Painter. You can do that, but there are also freely available PBR material sites. I advise you to do a quick Google search and discover them. Maybe you will find something interesting that will fit your needs. But you get the idea. Anywhere you go, you will get these maps: albedo, normal, roughness, metallic. Usually you will also get ambient occlusion, but we are not going to use ambient occlusion because ambient occlusion also in the newer game engines is calculated during real time. So you don't have to utilize ambient occlusion for your material workflow. That could be generated at a later time. But we're going to utilize ambient occlusion for different purposes and not use the ambient occlusion provided with the materials, but the ambient occlusion that is going to be generated from your object. We're going to look at it in a different tutorial. So in this list you will see lots and lots of different types of PBR materials that could be utilized in your projects. And most of these things, almost all of them, are fully photorealistic. And the best thing about these types of PBR materials in general is that they are procedurally generated, meaning that if you are interested into texture making, you could generate these materials without using any type of photographic references. In the old days, that is exactly what we had to do. We had to go in, find photographs, let's say bunch of bricks. Okay, so these are real photographic images. All right, here's a color chart for color calibrating the digital world to the actual world. Okay, so this is what we did in the old days. We would get these textures into Photoshop and try to generate roughness maps, normal maps, and metallicness maps and other types of maps, and then combine these with different types of photographic references to create layered materials. And that took a lot of time. I did that and it was fun, but it took a lot of time. So we don't do that anymore. We use PBR materials because it is much easier to generate a brick texture using only procedural data, and it could be highly realistic. This is not even a good material. You can do even better materials than this using procedural generation techniques in Substance Designer, for instance, or even in Blender. In any case, these are the types of channels that we are going to be dealing with. And before we go, let's look at it from a layer perspective. We're going to get into the details of this system, obviously, but as you can see under the layer stack here, we not only have these layers, but all of them are also controlled with base color, height, roughness, metallic, and normal maps. So you can switch this layer system to the different channels that it's right now controlling. Okay, so usually we work in the base color, but you should know that all layers here have the option to have these maps be activated and controlled separately. And we are not only that is the reason why Substance Painter and the PBR material workflow is, you need to understand the details of it, the background of it first before getting into it, because you should be aware of the reality that you're not just controlling the color of this surface, but also the roughness of the surface, the metallicness of this surface, and the normal directions of this surface, even the height of this surface. As you will see, we are not going to utilize the height map for the final result, but we are going to use it as an intermediary map to control the normal channels. In any case, this is how PBR Materials works. I'll see you in the next